Yes guys, so we are doing question number 8 now. In question number 8 we have some simple question here. We have to just find the mass of a plate bounded by y equal to 0, x equal to 0. These are two plates here, y equal to 0, x equal to 0. So these two lines are there, y equal to 0, x equal to 0. Y equal to 0 is on the x-axis, x equal to 0 is on the y-axis. These two axes are there. And x plus y equal to, this is a straight line, x plus y equal to 2. So these are the three things: straight line, x plus y equal to 2, and the two axes here, y equal to 0 is on the x-axis and y-axis x equal to 0. By these planes, y equal to 0, x equal to 0, and x plus y equal to 2, if it is bounded, so we have to find out the mass of the plate bounded by these planes, where density, its density is rho equal to density, rho equal to, its density rho equal to kxy. So rho density is kxy. So this we have to find out. So let me solve this question. Now up to now we have discussed these 7 questions in which we discussed about mass of a curve, mass of a plane lamina. What is the mass of a plane lamina in this case? Or in case of wire, the mass of this one. 6th one. A wire is in the, so this was mass of a plane curve, or a curve, simple, a straight line, or wire in this case. So wire is a plane curve. Now second point, third we have discussed about this one, 7th one, this is 3-dimensional geometry, or we have to find out, here it is given a ellipsoid, ellipsoid, 3-dimensional figure. This was ellipsoid was given x, y, z, there were 3 axes here, and kxy. So this was volume type of question. Then the 3-dimensional figure is given, or solid figure is given, then we have to find out its mass. So this was a solid figure definition, question based on solid figure. The tenth of this, find the mass of tenth of the ellipsoid. This one, 7th one. Now then, so all kinds of questions we have discussed. 8th question is again plane lamina type. Area of a square in this case. So area type of question when 2-dimensional figure is given. In this case, 2-dimensional figure is given. Question number 8, let me draw the figure here. What is given to us? We are given x equal to 0, y equal to 0, the other given figure. So first of all, we write what is given to us: x equal to 0, y equal to 0, and x plus y equal to 2. This is a straight line here. Let me draw this straight line to geometrical figure. This is x-axis, origin O, x dash, y-axis, y dash, y O, y dash. This is y-axis. This is x-axis. Geometrically, we know what this is. Now, x equal to, if I put here x equal to 0, y equal to 2, y equal to 0, x equal to 2. There is a straight line. Let me take this straight line like this. Here it is 0, x2 when y is 0. From this equation, so I substitute here y 0 on the axis of x, y is 0. On the axis of y, x is 0. So here it is the point 0 and 2. This is a straight line which is on which we have, let me draw a strip parallel to the axis of y. If I do a parallel strip parallel to axis of y, then what is the y limits here? The limits of y will be here y equal to 0, and on this line y is equal to 2 minus x from this equation. If I find out y here, y equal to 2 minus x. So on this, these two limits are of y. What is x limits here? X equal to 0. This one, if I draw this kind of parallel strip parallel to the axis of x, then limits of x coordinate will be x equal to 0. On this line, x equal to 2. X equal to 2 is a straight line here. So this passes to this point. This is straight line at which x equal to 2. So 0 to 2 is the x coordinates. Y coordinates are 0 to 2 minus x. Within these two periods, and density rho and density rho is also given. Density rho at xy points is equal to k into x into y. This is also given to us. Density is given to us. Now we have to find out the mass. I defined that what is the mass of a two-dimensional figure or plane lamina. Okay, so we give here the mass, capital mass of the whole figure. This figure, for example, which is a plane two-dimensional figure or in x y axis. Okay, this is straight line bounded by a straight line and these two axes. So area, first double integral here for x coordinate, y coordinate. Okay, and then rho into d.x.d.y. This is by definition we know that what is the mass of plane lamina. Rho into ds. Here ds is d.x.d.y. Alright, if I substitute limits, now x limits are 0 to. Okay, let me take 0 to. Here 2, 0 to 2. X coordinates are x here 0 and here it is x equal to 2 on this line. Okay, so x equal to 0 to 2, and second for y element, so y limits are 0 to 2 minus x. This is 2 minus x. 2 minus x here. Let me draw distribution. Okay, and now here rho. What is rho here? Density. K into x into y into d.x.d.y. Now we have to integrate this. Let me integrate this with first with respect to y, then with respect to x, because because first limits are from the right hand side. The first limit is for y coordinates. First we have to integrate it with respect to y. Let me write it in the proper manner. 0 to 2 in bracket 0 to 2 minus x. K, let me write here constant, which is constant here, and here let me write x into y into dy, and dx let me put outside for this bracket. So we are integrating here. Let me write it. Okay, this is okay. Now within bracket x y into dy, limits are 0 to 2 minus x for y coordinate. Okay, for y coordinate limits are 0 to 2 minus x by variable. Now let me integrate this. Integration of this will be 0 to 2. This is first limits for x coordinate. Okay, x variable and limits. Now integration of this will be x as it is. Integration of y upon 2, because we are integrating with respect to y. Limits are now 0 to 2 minus x into ds. Integration with respect to y of y is y square upon 2. Now dy and y change like this. Integration is done. Now putting the limits here in place of y 0 to 2 minus x, it will give us k into integration 0 to 2. Okay, x as it is. Now limits of y, putting variable y, the limits in place of variable y. It will be 2 minus x whole square. Now this 2 that we take outside. This 2 is not a square. We just in the denominator of this. So we have taken this outside here from 2 into y square is 2 minus x whole square. Now if I open this whole square, let me put 2 minus x equal to. Okay, integrating this with respect to, or if I open this 2 minus x whole square, then multiplying by x, then integrating, that can also be done. Now let me integrate this. So putting here k upon 2 as it is 0 to 2, let me open this x into 2 minus x whole square. If I open, it will be 4 minus 4x, sorry, this is 4 minus 4x plus x square into dx. Now if I first multiply by x and then integrate with respect to x, let me write here. Here n is 0 to 2. This one 0 to 2 here. Okay, and this we are writing. So k upon 2 is outside the sign of integration. Mathematical, this is 4x minus 4x square plus x cube into dx. Now integrating with respect to x, because x is here in all the values, I mean in all the terms. This is k upon 2, as it is integration of this will be 4x square upon 2 minus 4x cube upon 3, x square is integrated as x cube upon 3 plus x4 upon 4. Now putting limits 0 to 2, it will give us, this is k upon 2 outside, is 2 to the 4, 2x square. Now 2x square means x in place of x we have 2 here. This is 2 into 4, 2 square. This is minus 4 upon 3, x cube is 2 whole cube plus 2 4, 2 is over 4 and 4. So let me further solve it. It will give us final answer as k upon 2, right? This is 8 here, minus this is 8 for the 32 upon 3 plus this is 2 is over 4 means 16 upon 4 means 42. 2 is over 4 is 2 into 2, 4 times 4, 2, 2 into 2 means 4, 4 cancelled out, it's 4 only. Okay, now 4 and 8 12, it will be k upon 2, 12 minus 32 upon 3, 12 3 36, if I take LCM, 12, oh sorry, 3 LCM, 3, 12 3 36, 36 minus 32 upon 3, that means 4 upon 3, 4 upon 3 is 4k upon 2 into 3. So this is nothing but 2 to the 4, here is 2 is there, 2 to the 4, 2k upon 3, this is the answer here. 2k upon 3 is the answer of this mass, maybe in units may be kilogram, gram, whatever. But this is 2 twice k upon 3, and k is a constant of proportionality. As we always write it, rho is proportional to density is proportional to xy, so rho equal to k into xy. The rho is denotes symbol for that density here. K is constant of proportionality. So in terms of k, 2 by 3 k is the answer of this mass of this plate. Okay, plate in the bounded by that axis. I mean that straight line x plus y equals 2 and the two axes x equal to 0, y equal to 0 means x axis and y axis and x axis. That is the question number 8 we have completed. This answer here. Now let me take question number 9. What is the 9th question? Let me talk about that. We discussed about initially in the beginning, I mean definition part, that what is the mass of a plane curve. First we discussed about plane lamina, then plane curve, then curve, mass of a plane of an arc, I mean about an arc, mass of an arc or a curve. Then we discussed about what is mass of a solid figure. Solid means 3-dimensional figure. So that is there. So plane lamina means 2-dimensional figure. Curve is a single curve means arc. So mass of an arc. All kinds of questions we have discussed up to now. Now 9th question is also what kind of question is this? Find the mass of a group of the lemniscate r square equal to a square sine theta if rho density at any point of it is equal to kr square. Okay, let me take this lemniscate here. Question number 9. Now it says what is given to us here. We are given the curve is lemniscate is r square equal to a square sine theta. Okay, and density is rho. Density rho is equal to at any point of it is k into r square. If k times the distance of k is constant velocity, rho is proportional to r square. R square is the distance of any point on the lemniscate. Okay, from a pole, from its pole. Here the polar coordinates r and theta. In terms of r and theta, it is given to us. If a Lamina scale is this, then she can find the mass of a loop of Lamina scale is. Now let me draw the Lamina scale here. It's a loop of the Lamina scale. This loop is like this. If I take this in a equal manner, this is there. Here, okay, a line here theta varies from minus pi by 4 to plus pi by 4 theta. Okay. If I take any point on the Lamina scale here, P, let me take P and Q here, this is P. P r theta. Okay, P and r theta is given to us. Here r is equal to, okay, here r is equal to a under root. If I take square root of this, it will be a square root sine theta. Here r varies from 0 to, this is x-axis, y-axis, origin. This is pole here, okay, and this pole is O here. This is axis of the Lamina scale. So, and r theta we have taken as polar coordinates. Okay, so polar axis. Now, this is radius vector r. R is equal to, given to us, r is equal to a under root. If I take square root, this is sine twice of angle, but sine theta. Okay. Now, theta varies. This angle varies from minus pi by 2, pi 4, sorry, to pi 4, and r is equal to theta to 0 to, here it is 0 to r is equal to a under root sine 2 theta. This is square root sine twice of theta. Okay, the limits for r is this theta minus pi 4 plus pi 4. Therefore, mass in this case, again, this is two-dimensional figure, no problem. So, Lamina scale is given. Solution, let me find out the solution of this. So, here mass given to, mass is equal to double integral sign. If I put first theta angle, this is minus pi by 4 to plus pi by 4. Let me write directly. Okay, and then r limits are, the limits of r 0 to a square root sine 2 theta. Here it is rho. Let me write here rho into d r d theta dr. This we know about r dr d theta, because in case of polar coordinates, in place of d.x.d.y, we write r d theta dr. Why r is Jacobian. Value of Jacobian we have discussed in case of, okay, the previous, when we were changing the variable from coordinates to, another coordinates, like, okay, x coordinate to, Cartesian coordinates to polar coordinates. When we were converting into polar coordinates, then Jacobian was coming as r. If I take x equal to r cos theta, y equal to r sin theta, and then find out Jacobian. Jacobian is okay, integration or a differentiation of sine x and y with respect to theta and r. Then Jacobian r comes out. This are discussed in case of change of variables. Okay, this previous lecture. In the previous lecture, we have discussed this. So this is the total mass of this Lamina scale. The total mass, but rho denotes density of any point. Okay, at any point of this, or per unit of this Lamina scale, rho is given. Then mass is multiplied to the total area or whatever this value is given to us. Okay, in the double integral, this is area type. And area into mass, that means, sorry, density, that means mass. So density into area. This is how the area of the Lamina set is. Now let me put the value of r here. Sorry, rho is k r square. Now this, since we, let me use the one of the property of definite integral. What is that? Since minus a to plus a, fx or fx dx equal to twice 0 to a. This limit, if they are same limits but minus negative to positive, minus a to plus a, then it becomes twice of 0 to a, fx dx. It means we have to convert in this way, minus pi 4 plus pi 4 twice 0 to pi by 4. This is for theta variable. So theta has the limits minus pi 4 plus pi 4 in case of this lemon skate. Okay, loop of the lemon skate. Now come to the point. So this is 0 to a sine theta. R value or rho value is k into r square into r dr d theta. This is that. Okay, so let me take k constant outside. This twice k 0 to pi by 4. Okay, now limits 0 to a sine y theta square root of sine theta. Okay, this is r cube dr. Let me write this in the curly bracket into d theta. First integrate this with respect to r. What is this integration? And then substitute the limits. This is sorry. Here I put this curly bracket. Curly bracket is here. This to this. Only this is to be integrated. This is 0 to pi. Okay. Now integration of r cube is r4 upon 4. This is integration. We always add 1 in the given index. Okay, given power 3 plus 1 4 divided by the same additional limit now additional power. This is 4 here into d theta now. But limits are 0 to this a under root sine 2 theta. What the point? Now let me put the limits in place of r and then solve it further. Okay, it will give us mass. Let me write here mass equal to 0 to pi by 4. In place of r4, we have to substitute a under root. At 0 it will be 0, so lower limit is not required to be substituted. Only upper limit. It will be a4 of sine twice theta whole square. Why whole square? Because it will be 4 by 2. This is 1.2 power and this is 4 power. In place of r, we have to substitute this a under root sine 2 theta, then whole 4. Whole 4 means a4 sine square divided by 4. This 4 here. 4 I can take outside and k is also there. Twice k outside. Twice k. Limit 0 to pi 4. If I take 4 outside, this is twice k upon 4. Limits 0 to pi upon 4. Now, a4 is also constant, so I have to take it outside. a4 also I have taken outside. So this is twice k to the 4. Okay, so k a4 upon 2 now. 0 to pi 4 limits. Now this sine square 2 theta. What is sine square 2 theta value? We know that since cos 2 theta is equal to 1 minus 2 sine square theta. Right? Now this 2 sine square theta, if I take beside this is trigonometric identity. 2 sine square theta is equal to 1 minus cos 2 theta. That means sine square theta. This implies that is equal to 1 minus cos 2 theta upon 2. This is the value of sine square theta. But why we have to change it to multiple of angles? Because that can be integrated easily. The square cannot be integrated. So this sine square 2 theta we have to convert into multiple of angles. Now when it is single angle sine square theta, then it becomes 1 minus cos 2 theta upon 2, twice of angle. If it is twice, then it will be 4 times. Here it will be 1 minus cos 4 theta divided by 2. This is d theta. Sine square 2 theta is equal to 1 minus cos 4 theta upon 2. From this identity of trigonometry. Trigonometric identity this has given this formula. Now let me integrate this further. Our final integration of this will give us, this is k a4 upon 2. Integration of this 1, let me take this outside twice. Now integration of 1 minus cos 4 theta upon 2 is d theta. If I do integration of 1 is theta, cos 4 theta is sin 4 theta upon 4. It is nothing but k a4 upon 4 into the 4. Integration of 1 is theta minus, for the limits are 0 to pi by 4. Limits are also there. And so I forgot this. This is theta, 1 integration is theta, cos 4 theta is sine 4 theta upon 4 positive limits 0 to pi by 4 is the limits for this theta variable. Okay. Now we have to substitute the limits pi by 4 in place of theta. So what about this? This is Ka4 upon 4. Here pi by 4 in place of theta. First upper limit at 0 lower limit. Theta is 0. If I substitute lower limit, at lower limit both will be 0. Why? Because sine 0 is 0. So this at lower limit not required. What about at upper limit? This is minus sine 4 into theta, sorry, pi by 4. This is only sine pi upon 4. Sine pi is 0. We know this. So sine pi is 0. Therefore, final answer will be n square from this k into 8 upon 4 are there. From inside, it is only pi upon 4. Why? Because this is 0. Sine pi, since sine pi is 0, so sine pi because of sine pi 0. Since sine of pi angle 180 is 0, this we know sine pi here, sine 4 into theta, theta means pi by 4, 4 pi by 4, so to cancel out sine pi is 0. Finally, we have obtained pi into k into a 4 power divided by 16, 4 into 4. This is 4 here. I write 4 in the same way. That is 16 here. This is the answer. Pi k a4 upon 16 is the answer of question number 9 here. Question 9 is done. Okay, now let me discuss about 10th question. This is the last question of this. Okay, because these questions which are taken from students idea were okay. 8th question was different in the previous this time before, because that was given by one of the students, but there was some mistake there. So I have changed this question 8th. Okay, find the mass of a plate bounded by this. So 8th question by I changed from the previous one. Written there. Okay, now question number 10th, which is the last one. This is I think 3-dimensional figure. Okay, this is spherical figure. Find the mass of a solid in the form of the positive octant. This is a positive octant, means the first octant of the sphere is if the density at any point is kx by z. 10th question, this is the last one. Very interesting. Here, what are given to us? We are given here a sphere x sphere plus y sphere plus z sphere is equal to a sphere. This is given to us. Then density is also given, and density at any point of it, at any point of the sphere of it, rho is equal to rho, which is equal to rho equal to k into s by z. This is rho, we know density is rho, or we can write here, or rho equal to this, rho equal to kx by z. This is given to us. These two things are given to us. Now I have to convert this into spherical polar coordinates. So changing this into solution, let me changing the coordinates, Cartesian coordinates. Cartesian coordinates or spherical into Cartesian coordinates into spherical polar coordinates. Into spherical polar coordinates. What are those? Spherical polar coordinates. What is that? Here we put here x equal to, okay, we put x equal to r sin theta cos phi, y equal to r sin theta sin phi, and z equal to R cos theta. These are the spherical polar coordinates which we always do. Now, if I find out Jacobian of this, what the mass, I find out what the limits and mass that are. So here, because this is the first octant one. Okay, this is, I mean, this is three-dimensional figure I have to take, but in the first octant, for example, if I take what is the three-dimensional geometry, if I take one register here, and then suppose this is the point here, and below this there is axis, and above this is x-axis, y-axis, z-axis, okay, and below that again there is another space in which four dimensions are other. So there are eight parts of this. The whole three-dimensional figure, this solid figure divided into eight parts, eight octants. So one part is known as octant, one eighth of this whole space. So 1/8 of this sphere is only in the first, this one, positive octant, you say. The first quadrant, first octant, and only in the positive octant. Positive octant means here theta we will have theta equal to 0 to pi by 2, 0 to pi by 2. Phi is also 0 to pi by 2. Okay, if I take x, y dash and x dash, so and below this there is, this is above on the earth, and below in the space also there are four parts of this. Okay, so four parts below the space and four parts above. There are eight parts of this. In the first octant we have this. What is A? If I put these two x in x and y, z is 0. X and y, this one, z is 0. We get here for x coordinate, or sorry, r, here r, theta and phi, r will be 0 to a. This a is the radius of this sphere. 0 to a. If I take a part of this is one of the octant here, let me take a sphere like this. So this is one of the part of the sphere. This is spherical figure. This is a three-dimensional figure. So this is one of the octant here. Here, if I take the strip, the radius of the sphere is a, 0 to r is 0 to